Hello and welcome everyone. Thank you for joining today's webinar on an economic approach to configuring solar plus battery and wind plus battery hybrid energy plants. I'm Andrew Mills from the Berkeley Lab and one of the co-authors of this report. Today I'll welcome the speaker and also welcome Will Gorman, who will moderate the Q&A at the end. Before we get started, I wanted to go through a couple of housekeeping items. The attendees today will be in listen-only mode. So that means if you have any questions, you can enter those via the Q&A box that's on the bottom of your screen. We'll then set aside at least 15 minutes or so at the end of the presentation to answer those questions. If there are any that we don't get to, we'll try to follow up via email. Also, if you have any logistical questions, you can enter those via the chat and we'll be moderating that during this presentation. In addition, today's presentation will be recorded. We'll be posting a recording to our EMP website at the site that I'll enter into the chat here in just a second. The slides will also be available for that same link. There we go. So with that, I want to welcome our speaker and our moderator today, Cristina Crespo-Montañez and Will Gorman. Cristina is a Fulbright Scholar and a research affiliate in the Electricity Markets and Policy Department at the Lawrence Berkeley National Laboratory, where she works on modeling hybrid energy plants and battery degradation. As a PhD student in the Energy and Resources from UC Berkeley, she studies urban energy transitions, focusing on electrification and residential PV adoption policies in the backdrop of an increasingly disrupted grid. She holds a dual Master's of Science in Industrial Engineering from Universidad Politécnica de Valencia and École Centrale Paris. Prior to her graduate student studies, Cristina worked as a mechanical engineer in the Danish Technical University's Wind Energy Department and on PV development projects at the Spanish energy utility Iberdrola. Will Gorman is a researcher in the Electricity Markets and Policy Department at LBNL, where he's led research related to the development of hybrid, renewable plus battery projects. More generally, his work focuses on the integration of variable generation into the electric power system, the economics of distributed energy resources, and the application of energy storage within the grid. He holds a Master's of Science in Energy and Resources from UC Berkeley. Welcome, and I'll turn it over to Cristina now.
Hi all, thanks for joining the webinar today. I am Cristina Crespo, and I will be talking about our latest report that looks into the impacts of configuration choices on the recent economics of solar plus battery and wind plus battery hybrid energy plants. To situate this work, I will remind the audience that this is part of larger efforts stemming from the Electricity Markets and Policy Group at the Lawrence Berkeley National Laboratory that explore hybrids market value and historic development trends across the US. I will start by explaining the motivations for the report, go over the methodology employed in our research, present and analyze the results of our modeling, and highlight the implications of our simulated results as compared to current commercial activity. And I will finally wrap up with a summary of the key insights from our work. So hybrid power plants combining generation and battery storage are catching on. While definitions of hybrids differ, in our report we focus on variable renewable generators and battery energy storage systems that share a common point of interconnection with the bulk power system. The interest for hybrids comes from their potential to simultaneously, on the one side, perform energy arbitrage due to their dispatchability, and to participate in other remunerated markets such as ancillary services, all while being eligible to federal incentives such as the ITC and PTC, and also on expected balance of system cost synergies in comparison to the sum of standalone generator and standalone storage costs. These opportunities for increased flexibility, enhanced value, and reduced costs have aroused interest of developers, system operators, and researchers in understanding the economic viability and relative attractiveness of these plants. Interest translates commercially, as we see in this figure, into an increasing proportion of renewable capacity present in interconnection queues being paired with storage, shown in hatch portions in interconnection capacity increasing from earlier to later years on the x-axis for solar and wind generation technologies. However, not all hybrid plants are the same. Hybrids can behave differently than standalone renewables and standalone storage plants, and their behavior depends on the overall configuration parameters of the plant. Understanding, hence, the configuration of plants that are likely to be deployed in the near future is important for bulk power system planners responsible for ensuring overall system reliability and planning the transmission network. Yet, Because of the nature of hybrids, joining multiple components together, there are myriad potential configuration options for these plants, making it difficult to predict what hybrid plant configurations will come online. So we set out to explore, indeed, what hybrid configuration choices will really impact in a greater extent the attractiveness of these plants, and to better understand hybrid development trends. Indeed, there's not a consensus on the logic, criteria, or methodologies used by developers in designing these hybrids, and important factors in decisions are uncertain and changing, hampering our ability to predict what configurations are likely to be deployed. One common approach that can be used to understand and select hybrid design parameters in the top right of this slide is to define certain technical specifications and then identify the configurations that can meet those specifications at least cost. An alternative approach is to use capacity expansion models to identify hybrid configurations on the bottom right. These models evaluate candidate resources to find a portfolio that meets planning objectives, such as minimizing total system cost. Yet a few examples of capacity expansion models evaluate really a wide range of hybrid configuration options. Instead, we can use similar economic principles to find attractive candidates based on marginal analysis of system value, often represented or proxied by wholesale market revenues and costs in the left approach of this slide. This framework, which we use in our report, has been used in the past to evaluate variable renewables, storage, and most recently, in some cases, hybrids. An important note on our methodology is that we do not use it to explore why developers are choosing to co-locate storage and renewables, or whether hybrids are economically viable in the first place, but rather we seek to understand the trends in commercial development of hybrids that are occurring and identify factors that may alter those trends through an evaluation of the cost and revenues of different hybrid configurations, enabling planners to make more informed assumptions about the configuration and behavior of hybrids that will come online. So configuration choices that I've been mentioning include things like battery duration, battery power capacity in comparison to the generator installed capacity, the size of the grid interconnection capacity relative to the generator power capacity, and the size of PV panels relative to inverter capacity or inverter loading ratio, as well as the way in which batteries and PV panels are coupled together for solar hybrids. So let's look at how we set out to analyze across these configurations. We concentrate through our work on a specific indicator that we have called the hybrid net value metric, which we use to compare the relative economic attractiveness of different hybrid plant configurations. We construct this indicator as the difference between the optimal annual market revenues minus the associated costs for a certain hybrid plant. We normalize this indicator using the standalone renewable generation before curtailment of the hybrid plant to arrive to our dollar per megawatt hour indicator unit. So for each simulated hybrid plant, we calculate separately, as we see in these two boxes in the figure, the market values and the costs associated to the construction operation of our hybrid plant. On the one side, as regards to the market value of our plants, we first formulate a fairly simple linear optimization program, which, given some constraints on battery behavior, curtailment options, and different parameters for scenarios and configurations that I will later explain in detail, will dispatch against wholesale prices to get an optimal scheduling of a plant per year. And the revenue streams that these plants can dispatch into or can have access to include capacity payments and energy market revenue, and if applicable in certain scenarios, frequency regulation payments too for the battery portion. We choose to include a linear penalty in our objective function to limit charging and discharging of the battery or the cycling of it in the cases where arbitrage opportunities are small, to reduce the cycling and in turn the degradation of the battery. And once we have this optimal dispatch, we calculate more specifically the associated degradation to the battery given the cycling behavior, which has been shown to have a high impact on the operational lifetime of batteries. So in particular, what we do for this degradation modeling is that we extract from the time series of the state of charge of the battery throughout our optimization. We extract the number and depth of cycles of the battery using a rainflow counting algorithm, which is typically used to characterize metal fatigue. Then we use design curves for lithium-ion phosphate batteries, which is a common battery chemistry for utility applications, to map the different types of cycle to marginal cycling degradation, or the percentage of nominal capacity loss with each cycling. for the battery. And then we add to this cycling degradation that we calculate specifically for each each hybrid dispatch, a constant calendar degradation, which is a proxy for the degradation of the battery when at rest. And on the cost side, we calculate associated costs of construction and operation of the hybrid for each of the configuration choices, taking into account how the degradation calculation that I've just explained limits the operational lifetime of the battery when computing storage costs. And so we apply this framework to a certain number of scenarios and configurations. So I have already given a small summary of the configurations that we explore, but I would like to introduce also what we understand as scenarios in which our hybrid plants operate. So scenarios reflect exogenous factors related to technical, regulatory, or market conditions that frame the hybrid plant's operation, while in contrast, our configuration choices are endogenous choices made by the developer when deciding the hybrid plant. And we're going to be exploring hybrid net value across different configurations in hybrids operating in plausible scenarios. So in particular, we're looking at 4 types of variables to define these scenarios, in the exogenous scenarios, and 6 types of variables that look at the endogenous configurations. So we understand, for instance, for the scenarios portion, that hybrids will either be eligible to receive incentives or not. So in this case, we model ITC and PTC where applicable at 2020 levels, that the hybrid plants will operate under either a perfect or imperfect foresight of market prices and renewable resources, that they will have varying levels of a degradation penalty that we impose on the optimization of the hybrid, and that they will have access to either only energy markets and capacity payments, or also in certain scenarios to the ancillary service markets via frequency regulation payments. And our baseline scenario is basically chosen by choosing each of these variables, given it a certain value. So in our baseline scenario, we have no incentives being used, a perfect foresight of prices and renewable resource. We have a low degradation penalty of $5 per megawatt hour, and the hybrid participates in energy arbitrage and receives capacity payments only. Basically, all their scenarios will be generated by varying one of these 4 variables with respect to the baseline scenario, all else equal. Within these scenarios, we explore 6 types of configuration choices, which I mentioned earlier. So battery power capacity, that is that ranges from 25% to 100% of generator capacity, which we establish at 100 megawatts AC. So basically our batteries in our hybrid plants oscillate between 25 megawatts and 100 megawatts of storage size. Then the battery duration, which ranges between 2 to 8 hour durations, and grid interconnection capacity relative to generation power capacity, which in this case can either be just the generator capacity, so the 100 megawatts, or generator capacity plus the battery capacity, which changes depending on the cases. And then we also model whether we allow for the batteries to charge from the grid or exclusively from the on-site generation of the hybrid. And so we use all these configuration and scenarios in yearly simulations across a time frame that goes from 2012 to 2019. So conceptually, just what some of these configurations and scenarios look like. So on the top row left, we can see a schematic of a wind plant using perfect foresight of renewable resource and power prices, and maybe a schematic of a solar hybrid plant on the right, participating in real-time energy markets, but also frequency regulation markets. So those are different scenarios. And then in the middle row, on the left, we look at the size of the battery capacity in comparison to the renewable generation, all else equal. And then we can, in another configuration parameter, would look at the size of interconnection, all else equal. And finally, our lower row, we look at the coupling of the battery. So it's only for the solar cases, the coupling of the battery with the PV panels, in this case showing DC coupling between PV panels and battery, where there's a need of only one inverter. So having gone over what some of these scenarios and configuration looks and how they're constructed, we now concentrate on the selection of representative sites for modeling across the 7 ISO markets. So what do we mean exactly by representative sites? So to choose the sites, what we do is look for 3 things: sites that are already places where renewable plants exist of a particular technology, either solar or wind, and that they are close to most of the development of that technology in the region. This closeness here is established by the weighted centroid of installed capacity of that technology. So the axis on the maps are these weighted centroids of solar and wind capacity in each of these markets. And then we also look at the renewable resource of the selected site, which we characterize through the capacity factor of the site. We also look for it to be close to the weighted average capacity factor of the region for that technology. And closeness in this case is defined by a tolerance level of a 10% deviation from the average capacity factor of the region. So from our search, the 7 wind sites in blue dots and the 7 solar sites in red dots in the image are selected. Once we have selected these, we use historical wholesale market prices and weather patterns in these sites to evaluate hybrid net value across configurations in each of these sites as representative sites of the 7 organized wholesale power markets in the US. So we run in total over 100,000 hybrid scenario configuration year market combination of cases using our framework, and these are run on a high performance computer. So this is the methodological part. I'm just going to say again that if you have any questions about this or the coming slides, you can just put them in the chat as I present, and we'll go into them in the discussion section, but feel free to start asking questions in the chat. So as for what our results show. So first here, we show the resulting hybrid net values for all of our hybrid cases, that is for all of the combinations of configuration, region, scenario, and year, for the whole modeling timeframe of 2012 to 2019. The top we see results for solar hybrids, and on the bottom the results for wind hybrids. So the baseline scenario here is shown as a histogram and a box plot in green, while only the blue box plots are shown for the other scenarios. In the baseline scenario, so in green, we see that the median net value of all configurations, regions, and years is negative $22 per megawatt hour for solar and negative $14 per megawatt hour for wind hybrids. But even in this baseline scenario, which has no incentives, I recall, some hybrid configurations can be attractive investments. In particular, 20% of the cases have positive net values in the baseline scenario. Now, if we look at the deviation between the baseline box plot in green and each of the box plots for the different scenarios in blue, we see that scenarios that most impact hybrid net value are the scenarios where incentives are applied, and scenarios where the battery portion of the hybrids is allowed to participate in ancillary service markets. On the one hand, allowing storage to provide regulating reserves in ancillary service scenario, so AS, or the first row in each of the figures, increases the net value relative to the baseline scenario by $20 per megawatt hour for solar and $13 per megawatt hour for wind on average. While this is a significant increase, it is based on recent wholesale market prices, yet looking forward, regulation prices are expected to decline as more storage comes online. On the other hand, in the incentives case, so INCT, or the second row in this both figures, increases the net value relative to the baseline scenario by $21 per megawatt hours for storage and $9 per megawatt hour for wind. And these incentives are available to plants that recently became operational, though it should be noted that they are scheduled to step down to lower levels in future years. So the rest of the scenarios that change assumptions about foresight in scheduling dispatch, or the 4 case in the figure, the degradation penalty, or the DEG 0 and DEG 25 in the figures, and the disallowing or allowing grid charging, so the no GC in the figure, all impact net value for solar and wind hybrids by roughly plus minus $7 per megawatt hour. It is interesting to see that the higher degradation penalties, so the limiting of cycling of the battery, do marginally increase hybrid net value despite the loss in revenue opportunities from the reduced cycling, because they reduce the cost of the battery because of a slower degradation rates. So given that current and near future hybrids to be constructed are eligible to the incentives, investment tax credit, and production tax credit, the incentive scenario, and also that the incentive scenario leads to the highest net value for hybrids, the remaining results focus on this scenario. And before diving into configurational arrangements, we further look at historic trends in hybrid net value that you can see from lighter to darker colors in this figure. And we can see the hybrid net value in the y-axis across wholesale markets, And our results here are shown for the 7 ISOs in the columns. And we can see that indeed market trends are an important driver in the yearly changes in regional hybrid net value. Despite the different economics and operational profiles of solar and wind technologies, we indeed see very similar year-to-year variations when comparing solar to wind hybrids within the same region. And this is true with some notable exceptions. So firstly, in CAISO, which is the first column on both rows, between 2012 and 2019, the timing of high and low wholesale market prices shifted, leading to a significant decline of standalone solar value, which ultimately impacts the net value of solar hybrids despite their dispatchability, while the value of wind hybrids in the same market has remained steady. Secondly, high wholesale market prices in summer afternoons in ERCOT in 2019, associated with low planning reserve margins, increased the net value of solar hybrids, as seen in the second column, relative to the increase in net value of wind hybrids in ERCOT 2. Now, let's turn to the configurations exploration. Again, configurations differ from scenarios in affirming that they are endogenously decided design parameters chosen by developers. So we look again at the incentive scenario throughout, and we will be looking at hybrids that are using a perfect foresight into market prices and renewable resource, and a small cycling degradation penalty of $5 per megawatt hour. And throughout the generator capacity, again, is 100 megawatts, as explained before, and we will be averaging the results from our 2017 to 2019 timeframe to better capture recent market trends, but also attenuate the effect of outliers. So we'll go through the next 3 slides in order of the most to the least determinant configuration parameter in terms of how their choice impacts hybrid net value. So in this figure, we show the configuration parameters that most significantly impact hybrid net value, which are the storage duration in the legend. Lighter colors are shown to be longer durations, and storage capacity, which we see in the x-axis for the 7 markets. Our hybrid net value indicator is in the y-axis as before. In the top row, we see the solar hybrids, and the bottom row, the wind hybrids. We start by comparing the net value of hybrids to the net value of standalone wind and solar generators, which are represented in the figure as a configuration with 0 megawatt battery. And for the majority of the regions, what we see is that the net value of at least one hybrid configuration exceeds the value of the standalone generator, with the exception of standalone solar exceeding net value of solar hybrids configurations in MISO, and standalone wind exceeding the net value of all wind hybrids in MISO, PGM, and New York ISO. Attractive solar hybrids are more common than attractive wind hybrids in the incentive scenario, possibly because of the tax incentive used by solar, the ITC, reducing the capital cost of the batteries, whereas the tax incentive used typically by wind, the PTC, does not. Hybrid configurations with the highest net value have throughout 2-hour duration storage, as we see in the darker points. And this essentially points to the fact that currently battery costs associated with increasing the duration of storage outweigh the associated increase in market value, particularly for large capacity storage, as you move to the right. In terms of battery capacity, hybrid configurations whose value exceeds standalone generator tend to have storage capacities at one of the extremes, so either 25, which is the minimum that we modeled, or 100 megawatts, which is the maximum that we model. In the case of wind hybrids, for instance, the smaller the battery, the higher the hybrid net value throughout. Yet for solar hybrids in CAISO, SPP, and ERCOT, high capacity storage batteries, the 100 megawatt storage configurations, are more attractive in the incentive scenario. And more generally, the more battery capacity that is added to 2-hour duration solar hybrids, the more the net value increases. Although this effect does disappear when no incentives are applied. Across these 3 regions, the net value of solar hybrids with 100 megawatt battery capacities can be at $3 to $11 per watt hour higher than the net value of standalone solar. And for a specific battery duration and battery capacity, what is left, or the remaining variation for the net value, which we can see here as the differences in height of the dots with a similar duration and capacity, which of these columns within the market column, comes from the choices in the point of interconnection capacity, the coupling, or the inverter loading ratio in the case for solar hybrids. And these are the 3 configuration choices that we'll now see in turn. So in this slide, we turn to look at the point of interconnection effect, which is less important than the battery size and duration, but is still a significant factor in hybrid net value. We use here the term POI effect to refer indeed to the difference in net value between a hybrid configuration with a POI capacity equivalent to the sum of the generator and the battery capacity, and the net value of an identical configuration of a hybrid, except that the POI capacity is equivalent only to the generator capacity. And we look here at AC coupled solar and wind hybrids. So in general, what we see is that increasing the point of interconnection to the sum of the capacity of the generator and the battery typically increases the net value relative to otherwise identical configuration with a lower POI capacity. For solar hybrids, we see that the POI effect increases with larger storage capacity and with longer storage duration. And within the regions, the different market regions, we see that there are 3 with greatest value changes with POI capacity. So this is true for the solar hybrids for ERCOT and SPP in the top row. We see that these 2 regions are places where either peak summer afternoon prices in ERCOT or high bilateral capacity prices in SPP are significant contributors to net value of the solar hybrids. Having extra POI capacity hence allows solar to produce at full output at the same time as the battery is fully discharging. And the POI effect is even larger for batteries of 4 to 8 hour durations, the lighter dots that we can see here, because with longer battery durations, there are more time periods where limiting the POI capacity can prevent storage from being fully dispatched simultaneously to solar production. However, even if this POI effect is larger, we have already said before that 8 hour duration batteries still have a lower net value than hybrids with 2 hour duration batteries, irrespective of POI capacity. So an order of magnitude, hence, for this effect, for an AC coupled solar hybrid with 2 hour duration batteries and 100 megawatt battery capacities in ERCOT or SPP, we're setting the POI to the sum of the generator plus the storage capacity in 200 megawatts in this anecdotal example, increases the net value by $8 to $11 per megawatt hour relative to the same hybrids with a POI capacity of 100 megawatts, which is the generator exclusively. For solar hybrids in CAISO, in the first column, we see that the extra POI is relatively less important as peak prices shifted towards the early evening, away from the times of peak solar production. Interestingly, recent peak prices are shifting to higher wind production times, making extra POI capacity more valuable for CAISO wind hybrids in the lower row than wind hybrids in other regions. Indeed, we find relatively limited impact of increased POI capacity for wind hybrids otherwise, as shown here in the bottom row. And in regions like MISO, ISO New England, and New York ISO, extra POI capacity actually reduces net value because the increased interconnection cost exceeds the increase in market value. And this increase in market value is minimal either because capacity prices are low, that can happen in MISO, or because high prices rarely occur at times of high wind production. So you can allow for fully discharge of storage at times of high prices, even without an extra POI being paid. And so moving now to effects that are somewhat secondary in comparison to the POI, the battery capacity, duration, and POI capacity, and exclusively for solar hybrids, we turn to look at coupling strategies, so AC versus DC coupling of batteries and PV panels, as well as the inverter loading ratio level for these hybrids. We concentrate in this figure, again, in this figure, particularly on 100 megawatts storage capacities. So here, these are plants of 100 megawatts generator plus 100 megawatts storage capacities. These are secondary considerations, again, in comparison to what we've spoken about earlier. In the top row of the figure, we plot here the differences in net value between a solar DC coupled hybrid plant and the net value of the identical configuration, except with an AC coupling. And what we see is that with the exception of ERCOT and SPP that show negative values, the DC coupled configuration have a higher net value that increases with ILR, shown in the x-axis, than otherwise similar AC coupled configurations. So this is shown here as positive values in the figure. And DC coupling allows the battery to capture energy that would otherwise be clipped by the solar generator's AC inverter. So as the ILR increases, more and more energy is skipped by an AC coupled system, driving the relative increase in the net value of the DC coupled system compared to its AC counterpart. However, developers would not necessarily go into high ILR levels for this for AC coupled hybrids in the first place. Hence, we look in the bottom row exclusively at DC coupled solar hybrids to understand the ILR effects with more detail. And we see here only concentrated on the 2-hour duration batteries, so the darker lines in the lower row, that an ILR of 1.3 has the highest net value in CAISO, ERCOT, and SPP, and an ILR of 1.7 in MISO, PGM, and NISO, and ISO New England also has the highest net value. So higher ILRs increase net value with the 4 to 8 hour duration batteries, although again, as we have discussed earlier, the overall net value of these longer duration configurations is still lower to the 2-hour duration. What is a surprising finding here is that the net value decreases with ILRs larger than 1.3 for 2-hour durations in CAISO, ERCOT, and SPP, but do not do so for the other cases. And even though market value increases by capturing otherwise skipped energy, there are additional costs also associated with more PV panels and an increase of battery cycling. So this increased cost on the one side of the PV panels at high ILRs is potentially not offset by a corresponding increase in hybrid revenues in these regions. And furthermore, and as explained earlier, cycling more energy at these higher ILRs through storage will not always improve the net value, depending on the impact it has on battery lifetime. In contrast, as I was saying, the results in MISO, PGM, and NISO and ISO New England show marginal gains when increasing from 1.3 to 1.7 for DC coupled solar hybrids with the 2-hour duration batteries. And these marginal gains actually disappear when we look at absolute value market revenues minus costs instead of our normalized hybrid net value metric that uses the pre-curtailment AC VRE generation as a denominator. One hypothesis, however, for these different trends in CAISO, ERCOT, SPP, and the other markets, regardless, could be that the shape of the net load in these areas is different. So regions that with sharply peaking net loads like CAISO, ERCOT, and SPP would benefit more for power delivered at critical times. So solar hybrids with higher ILRs, even at higher ILRs, might limit the high value opportunities in these specific times, while regions with smoother net loads on the other hand, like MISO, PGM, NISO, New York ISO, and ISO New England, would continue to show higher net values for increased production from otherwise skipped energy as ILR increases, even if it is delivered in non-critical shoulder hours here. So having explored these results, we turn to look at how these results can help us understand recent trends in commercial development with regards to hybrid plants. And to compare our economic framework to commercial hybrid development activity, we will be studying 3 sources of qualitative data. So the characteristics of hybrid projects deployed across the US, hybrid plants that have secured offtake, and active hybrid projects in interconnection queues. The data that we consult comes from recent work from some of the authors of this report and other lab colleagues on the status of installed and proposed hybrid projects. Overall, what we see is in our qualitative comparisons between our results and commercial hybrid activity is that our analysis of net value of alternative hybrid configurations can help corroborate observed trends and can yield insights into how trends can change under different scenarios. For instance, our results show that higher net values are present for solar hybrids in comparison to wind hybrids. And the data we consulted shows solar hybrids are more common than wind hybrids. Our results also show that shorter storage durations are most attractive, while commercial projects typically have batteries in the range of 1 to 4 hours. Both our results and the data consulted show storage to generator capacity ratios that are larger for solar than wind hybrids and are largest for CAISO. And across technologies, Data consulted shows solar and wind are most common in CAISO, with substantial commercial activity in ERCOT and SPP, which are the 3 areas where results show hybrids are most attractive. In certain areas, however, our results disagree with commercial activity. In particular, hybrids in CAISO interconnection queues have a point of interconnection capacity similar to the renewable generation capacity, while our simulated results suggest a greater value by increasing interconnection capacity to the sum of the generator plus storage capacity. Reasons for this disagreement could be that actual interconnection costs are higher than our assumption, that interconnection rules make it easier to add storage to a project in the queue without submitting a new queue request if the original point of interconnection capacity is respected, or developer expectations that the storage will not need to simultaneously discharge during times of solar production in the future as PV penetration increase. Anecdotally, however, we have seen in our sensitivity analysis that earlier years of simulation show greater point of interconnection effects than later years of a simulation that we showed just before. So to conclude by putting together some of the main messages, and I will give some insights from the project. We see that wholesale market revenues and battery cycling dynamics and bottom-up cost calculations can be used together to understand the relative attractiveness of hybrid resource options. On the one hand, across scenarios, we realize that the inclusion of incentives and increasing revenue streams, regulation, service provision are the most attractive scenarios for hybrids to operate in. And on the other hand, when exploring different configuration options in our report, we find that storage duration, capacity, and POI capacity effects are most important in that order, and other parameters are secondary. In particular, as for configuration options, storage duration and storage capacity have largest impacts. Attractive hybrids typically have 2-hour duration storage. For solar hybrids, storage capacity with the highest net value can either be 25 or 100% of solar generator nameplate capacity, depending on the region, although only the smaller storage capacity is attractive in the absence of investment tax credit. In contrast, all the highest net value wind hybrids are those with the smallest storage size, that is 25% of wind capacity, with or without the availability of production tax credit. We find that it is more attractive to set the interconnection capacity to accommodate simultaneous discharge of the generator and the battery, as opposed to limiting the interconnection capacity to a generator power rating, particularly for solar hybrids in ERCOT and SPV markets, but less so in the case of wind hybrids. In comparison to all of these configuration options, the choice of coupling for solar hybrids, that is AC versus DC coupling, and the sizing of the solar panels relative to the inverter, again in solar hybrids, appears to be secondary. Overall, our results do corroborate commercial trends in as far as we have information about them, showing that our framework provides a tool to understand market-specific insight into how these very trends can change under different plausible scenarios. With that, I would like to end our presentation and open up for discussions and any questions. Thank you for listening in today.
Great, that is awesome, Christina. Thank you for the presentation. And so now I'm going to help lead and moderate the Q&A session. So this is just a reminder, we have 20 minutes of time now, and there are a number of questions already kind of in the Q&A chat, which is great, but definitely encourage folks, if you do have any burning questions, anything that comes up, please include them in the Q&A now, and I will be moderating them and organizing them. So let's start with some methodological questions that have come up in the Q&A. And there have been a few questions, some of which we've answered, but there's still a few more came in about really the underlying metrics that we're using to analyze these hybrid resources. So the metric being this dollar per megawatt hour value that we showed on all of these charts. And so one question is kind of just on why we chose that particular metric rather than using maybe something like the total costs and the total revenues of these hybrid technologies. And in particular, I think some folks are just a little confused about how we have incorporated the costs of batteries in our cost calculations. And so just given a little bit of clarity into that net value metric, I think could be a useful place to start.
Okay, yeah, definitely. So one of the reasons that we thought about this net value metric in relative terms was to be able to easily compare across some of our configurations, and initially also to always have a way to compare back to standalone generation if needed, although that is not the main objective of the report. And in the way that the construction works, or how the battery storage costs are part of the metric, is that we've calculated completely independently the market revenues. So only we have positive revenues for when we're discharging, and then we have negative revenues when we're charging from the grid, for instance. But these are all defined in revenue terms, and then we use annualized, so close to a levelized cost of the generator and storage portions, but rather an annualized in this case cost of the storage and the generator, to create the cost metrics on their own side. And then once we have the total revenues and the total costs, we normalize them together by the pre-curtailed AC generation of the plant. So within the cost calculation, what we have is capital costs and operation costs for the generator, and capital cost and operation costs for the storage, and we add them together, and we use a hybridization reduction factor in the capital costs of these two assets that we take from previous literature, although there is some uncertainty around this reduction factor, and we have run some sensitivity cases that are shown in the report. And again, within the storage costs, more specifically, the way that we account for the lifetime of the battery includes the degradation analysis that I went over. That I can further explain it. That there's a question specifically on that.
Great, yeah, thanks, Christina. And I think just to be a little more specific to that person's particular question, I would say that this report is about hybrids more generally and the costs and value of those, and we weren't explicitly focused on the additional value per se on the battery component in particular, but we do have other reports on our website that look a little bit more at the value of adding storage to VRE, but our focus here really was on hybrids. Okay, great. So another methodological question. In the solar modeling that you do, how is clipping managed? So how do we take into account this clipping that comes from the inverter? And how might that change the capacity ratios? So I think, yeah, how do we kind of incorporate this clipping issue?
Yes. So basically, what we do, so for the DC cases, what happens is that the clipped energy can be stored in the battery before the inverter. So basically, the layout of the plant and the virtual twin of this layout allows for the DC produced energy to go into the storage, and then from there we have different levels of inverter loading ratio of the joint solar and storage. And however, in the AC case, the clipping energy is lost because there is an inverter. So there's the PV panels and an inverter, and the clip energy is lost there, and it is only once it has been transformed into AC that then it's further transformed by the storage inverter in its turn to be saved in the battery. So in the AC cases that is lost, and in the DC cases it is conserved, and that is why we see in some of the figures that I was showing previously that indeed in this DC cases you do see an increase in the hybrid net value, but just not as important, maybe as changing other parameters.
Great. Another quick question on methods. There's a question on what incentives we were specifically referring to.
Yeah, definitely. So basically, when we're talking about incentives, we look at solar. In the case of solar hybrids, solar and battery get a 26% ITC incentive. So investment tax credit, and wind gets the higher of either an $18 per megawatt hour production tax credit or an 18% level of ITC for wind and battery, and that is according to 2020 levels. And more specifically, when solar and wind hybrids get the ITC, we restrict the charging of the battery to the on-site renewables. And in the other case, though, when wind receives the PTC, it is allowed to charge from the grid. So in the wind cases, basically we just decide which incentives makes more sense, depending on whether it makes sense for the hybrid to restrict or not grid charging.
Okay, great. And this might be one of the last more methodological oriented questions. There is a question about, is the extra point of interconnection capacity that we model, is that just extra capacity on the transmission line? Or does it have something to do with the more complicated request for nameplate capacity of the storage and solar and wind system? So I think the question is, how do we ultimately think about the point of interconnection capacity in our modeling?
So if I understand the question correctly, I think the point of interconnection capacity in our case is simply the maximum allowed capacity that interfaces with the grid, to say it like this. So we just limit basically the amount of power at each step of time that we can actually interface with the grid at, and otherwise we have just lost power, or we restrict the battery to not discharge at that point. I don't think it is not more complex than that. And that point of interconnection is limiting technically, but also we include a payment to increase that point of interconnection. So there is a cost part to that, to increasing that point of interconnection too.
Okay, great. So let's get into some of the questions that are more on the results side of your findings. So the first one is a question about why the solar hybrid net values were negative in MISO and New York ISO. And the question here is, do they not pencil out in these markets?
Yeah, so again, I would want just to reiterate that we have not set the methodology to respond to whether hybrids are valuable per se or not, but rather stemming from the fact that they are coming online in many places. In which ways can they be more or less attractive? But indeed, looking more like in absolute terms instead of across hybrids, we do see in those two markets mentioned mostly negative values for across configurations. So these can come from either this can come from the timing of the high prices, for instance, and these can also come from the storage costs still being too high for the relative arbitrage opportunities in those markets. Again, like other studies have shown, the introduction of storage typically makes sense in places with very high arbitrage opportunities. So that can also lead to some of these markets having lower attractiveness across hybrids.
Great, and I think I missed somewhat more of a methodological question that we'll get to right now, but in the AC versus DC coupled net value results that you were showing, were those results calculating just the energy value, or were we including capacity and ancillary service value as well? In
the AC versus DC, we're only including the energy markets. So in the scenario that I've been using throughout this configuration breakdown, we are only including energy payments. However, we have done some sensitivities for other cases, but not for the AC-DC comparison.
And I think we also, is it true, we also have capacity payments in there as well?
Oh, yes, sorry.
Yeah, okay. Yeah, I think it's the ancillary services we don't include in the baseline results. Great. Okay, so now we have a question on CAISO in particular, and it's one in which our study may or may not be relevant to, but I'll ask you here. And this person asked, what is our take on developer preferences for the hybrid configuration in CAISO specifically? And I think they're referring to the fact that there's this choice about whether you could choose between one resource ID. So the CAISO is only looking at, you know, the hybrid resource. It doesn't really see a set standalone solar or storage unit versus having two resource IDs where those are more modeled separately. The question is, do we expect hybrid configurations with one resource ID to be a major market development angle going forward? And does our work at all speak to some of those questions?
I unfortunately, I don't think that our work really speaks to those directly, because I think there are some from our side invisible choices or costs into going to the one resource versus two resource ID question for developers. We have, and in all of these cases, we have assumed that we're interfering with we're interfacing with the market directly, but not really looked into what the typology of the plant or the regulatory obligations or reporting obligations would be, and how those would impact the choice of the developer. And if I understand correctly, those can differ from the one resource to the two resource ID. In this case, I think all our simulations are most resemble the one resource ID case that we show here. But I'd be happy to talk further to that maybe.
Yeah, no, great. And the only other thing I'll add is we do have some analysis that goes into a little bit more depth on the commercial activity. And we actually have a slide and a report that I can put in the chat that talks a little bit about what CAISO developers are choosing at this point. And it seems so far that a lot of them are choosing this co-located or two resource ID model, but obviously that kind of decision might change and is very dynamic over time. But thanks for the question. So I'm gonna go to another question on POI in our results. And so this question says, a larger POI was pointed as a key variable that affects the hybrid valuation. We also mentioned that regulation and other AS could decrease as the price as more storage and hybrids come online. Have we evaluated or considered evaluating a need for the evolution of the ancillary service definition to allow for more storage facilities in the grid?
So in our modeling, we don't. So basically, we use historic prices throughout. So even though in the results that I've been showing, we've mostly been focusing on extracting conclusions from the latest modeling years, we do limit ourselves to the market prices that are out there right now. And so indeed, we can be showing dynamics or trends or underlying factors that could disappear if those prices change significantly in the case of AS markets. I would say that in order to palliate maybe the effect that can have, we have tried to de-emphasize the AS portion in our exploration of configurations that really looks at only capacity payments and arbitrage in energy markets, due in part again to this thinning of the AS markets as more storage comes online. And I would say, though, we've not shown here, but it is interesting to say that AS markets do have, in our calculations, do show to be important scenario change, and also have implications on ideal configuration parameters. So we typically see higher capacities in scenarios where AS revenues are allowed because of the capacity payments of frequency regulation services, for instance. So definitely, as they change, some of the trends will change, and we've tried to sort of to reduce their effects on our conclusions by not looking into them too much when exploring configurations across hybrids. But I would point to some of the supplementary information in our report where we look specifically at the ancillary service scenario.
Great. Thanks, Christina. So we have 2 more questions. I think we'll have plenty of time to get to both of these. But if there are any last minute questions you have, feel free to put them in the Q&A, and questions we don't get to, we do try to follow up via email. So it's never too late to put a question in. But I have another question here that is more broad, looking beyond this study, wondering if you have any thoughts on the challenges to making long duration storage economic, given I think some of the context here is that a lot of people talk about the need for long duration storage, especially in high renewable penetration grids, of which we don't isn't focused on this own research. And so just based on your kind of study of the costs of these storage technologies and maybe what you model, if you have any thoughts on long duration.
So
storage.
what we do in our report for cost wise, or how we included duration in our cost analysis, is that we've used PNNL's database on storage costs that discriminates according to duration, and you can clearly see that at higher durations are non-linearly or more costly than lower durations. And so we can, I would say that one of the easy ways to back engineer from our framework would be to establish the level at which the price per kilowatt and price per kilowatt hour for the battery costs would be needed, or what level would be needed in order to make some of this longer durations more economic. So here again, we only look at this economic perspective. So we would just see that the costs are very high, and even when allowing for greater market opportunities with that long duration storage, they just don't. They're just not worth economically what the storage duration costs. However, what we could see as changing is if duration is highly valued or socially valued, or the system highly values longer duration in this high renewable penetration cases, then some of the market conditions should change such that there is a market opportunity that would pay for this higher or longer durations. And so, for instance, things like again, ancillary services or payment or capacity payments that would be geared towards longer durations could be a way of having those longer durations, despite their cost being more costly, also having greater market opportunities. But in what we're seeing right now, or what we're valuing in the market, does not necessarily map to the higher duration storage cases.
Great, thanks, Christina. There are 2 more, I think, questions you can answer very quickly, but then we are at time. And so maybe I'll just ask these 2 context questions, and then we'll end the session. So the first was Hawaii included, and would we include it in the future? And then the second is for the capacity and duration study, the analysis that we did we look at AC and DC coupling?
Yeah, so the Hawaii was not included in this study. We're really only looking at this 7 ISOs and duration and capacity. So the duration and capacity studies, I think that I just mentioned, I suppose is the question, we're only looking at storage at storage costs. So they were not based on AC or DC coupling systems. Does this?
Yeah, I think that's right. I think we do look at AC and DC coupling in the study generally, But yeah, maybe not in this specific thing that you mentioned here. But we are at time. Feel free to reach back out to us. If you have any questions, our emails are on our website. If you look at Lawrence Berkeley National Lab and Google our names. But thank you for joining. And we look forward to seeing you on future webinars.
Thank you, everyone.